Welcome back. Good morning. So today we have, I'm starting and I'm going to talk about protoplanetary disks. And then after the break, Charles is going to be taking over, talking about black hole accretion. So there's going to be a big range of energy scales today. Okay, so Sasha asked me to discuss protoplanetary disks. So this is definitely the low point of the school in terms of energy. So we're going to be talking about 10 or 100 Kelvin gas, so very low temperatures, very low energies. And then after that, we're going to be moving to black holes, and then tomorrow we're going to be going to plasmas and things like that. So one of the nice things about protoplanetary disks is that we have some very nice and recent images of those systems. So we should start with this. These are images from the D-Sharp survey, which was published last year. It's just a subset of the systems that they looked at. And these are images made with ALMA. So this is radio emission at a wavelength of about a millimeter. So what you're looking at here is emission from dust in these disks. Scales here are 50, 100 astronomical units, in some cases a little bit larger than that. And the sort of striking thing and the main result of this survey, which many of you will have seen, is that there's a lot of non-trivial structure in these systems. Okay, so they're not purely radially smooth declining profiles of dust surface density emission. Instead, in many of these systems, you see these rings of emission, and then in some of them, you see some other kinds of structure. Some asymmetries in the azimuthal direction, or spiral arms, and so forth. Okay. So this is what we're talking about. We're talking about disks of gas and dust surrounding young stars, lasting for maybe a few million years, and presumably within which planets are forming. Okay, so there's sort of at least two different reasons why we might be interested in those systems, which have sort of motivated my choice of which things about protoplanetary disks to talk about in this school. So one aspect is that these are accretion disks. Okay, so we can actually observe indirectly, but with high confidence, gas flowing through these disks and being accreted onto the star. And the typical accretion rate you might get here is something like 10 to the minus 8 solar masses per year. Okay, so over a few million years, you would accrete a significant or a non-negligible fraction of a solar mass. And presumably at earlier times, the accretion rate would be higher. So these are accretion disks, and specifically they're examples of geometrically thin accretion disks, in the sense that if we look at the vertical structure of the disk, the vertical scale height is a small fraction of the distance to the central star. And it's not a vanishingly small fraction in these systems, so value of 0.05 might be a fairly typical number. So it's a thin structure, but it's not an absolute sheet like something like Saturn's rings. Okay. And there are other accretion disks which have that same property. That's sort of in some sense the classical example of accretion disks that have these thin structures. There are also examples of geometrically thick accretion disks, which we'll be hearing more about in the context of black hole accretion. So these are accretion disks, and from that point of view, the nice thing is that these are systems which can actually be spatially resolved. Here you have 8 examples of those of that imaging. Okay? And not only can they be spatially resolved, if you look in molecular line emission, so this is dust emission here, but you can also look in emission of molecules such as CO, HCO+, other species, and by looking at those molecular lines, you can measure the velocity, in principle, at each point in this image. So you can have both spatial resolution and also spectral resolution or velocity resolution. So that's that's a unique situation in the context of accretion disks, and gives a way to maybe say something about what's going on in accretion disks. Okay, how much turbulence there is, questions like that. And then, of course, the second reason you might be interested is as an environment for planet formation. And as many of you will have heard, there's a popular interpretation that these rings, in particular, that you see in these images, are actually due to planets. And the basic sort of idea would be that here in this system, somewhere here, maybe here, there's a planet, perhaps with masses comparable to Neptune in the solar system, something like that. And what you're seeing here is that that planet has excited waves in this disk and is trapping dust particles sort of in the regions between those waves, roughly speaking. Okay. So there's obviously a lot of questions there about, well, first of all, whether that's the correct interpretation of this data, and if so, what that says about how quickly planets are forming in these systems. Okay, so we won't get into those interesting questions. So based on that, what we're going to talk about today is sort of two topics. One, which is, in what sense are protoplanetary disks just like other accretion disks, and in what sense are they different? At the center of this whole system? Yeah, so here you have a young star. So the systems we're mostly thinking about are stars with masses similar to the sun or somewhat lower. Okay, so the situation is a little bit different if you were thinking about very massive stars, which would have a very large ionizing radiation output. So here we're talking about mostly low mass stars. And in these sort of images, you should sort of think of the star as having acquired most of its final mass, but not yet having a main sequence stellar structure. So it's still got some way to go. Right. So the question is how you measure the thickness. Well, so here you're not sort of getting at the thickness directly. There are other classes of observations where you can, for example, see the disk edge on, and you see scattered light from the upper and lower surfaces. So there you can relatively directly get at the thickness. You can actually get at the thickness from images like this as well, but that's a modeling exercise rather than a sort of direct read off the image. Probably actually. So this is emission from moderately large particles. It's not really tiny dust particles. So probably actually the emission is actually thinner here than the gas. That's the general interpretation. So here there are not so many companions. So these would be basically remnants of clumps in a molecular cloud after it's collapsed. So the sort of picture you would have is a large molecular cloud, maybe with hundreds of thousands of solar masses and material, but then the clumps in that have collapsed down, and this is the material with angular momentum that has formed a disk around it. So these are transient structures that are sort of left over from the star formation process. So it's generally thought to be, let's say, of the order of 3 million years, 5 million years, maybe up to 10 million years. So that's, let's say, if we just say it's up to 10 million years, no one is going to argue with us too much. If you get to whether it's 3 million years or 5 million years, the difficulty is that it's quite hard, very hard, to put an accurate age date on a young star. So you can have some uncertainty due to that. That's a tricky question. So how the properties vary with mass is measured, I would say, but not very well understood. So for example, I think the most secure result is that if you measure the sort of typical accretion rates as a function of stellar mass, those have a scaling that is steeper than linear, which is sort of not an obvious thing, right? And what that really says, whether that's saying something about how the disk is evolving or more about the initial conditions or what it was like when it was formed, is not a completely settled question, I would say. Okay. So yeah, so there's sort of two things we can talk about which are related to these issues. So one is, in what sense are protoplanetary disks accretion disks? like other accretion disks, and in what sense are they different? And the obvious reason that they're different is that they're very cold. So we're saying, if you're close to the star, you might be dealing with obviously temperatures that are similar to stellar photospheric temperatures, so few thousands of degrees Kelvin. But then if you get out to 100 AU, the temperatures are more like tens of Kelvin, or even 10 Kelvin. Okay, so very, very cold, and therefore very weakly ionized. So in the context of what Blakesley was talking about yesterday, we're sort of below the bottom of the plasma part of her plot in the region where the ionization fraction is very weak. Okay? And it's interesting that MHD is sort of valid at all in that region, and we'll be talking about how that goes. And then the other thing is, one of the main reasons we're interested here is making planets, so making solid objects mostly, right? Things like the Earth. And we also observe a lot in dust. Okay? So we've got gas and we've got dust, and in interesting regimes, those are coupled together aerodynamically. Okay? So there's really just aerodynamic coupling between solid particles which are moving relative to the local gas frame. So we have a two-fluid system, if you like, where one fluid is gas, the other is dust, it's pebbles, maybe later it's planets, which wouldn't have aerodynamic interactions, but would have gravitational interactions, and we can be interested in how those things play together. Okay. So those are the topics we're going to discuss. So we're going to start with discussing non-ideal MHD, which is a large topic in its own right. And I think what I'm going to try to get through today is to give you at least a sketch of how the equations of MHD, which we've already discussed, ideal MHD, are modified when we have this low ionization fraction, which is very, very characteristic of protoplanetary disks. As you were hearing yesterday, this also takes place in star formation, but in a slightly different regime, right? So star formation, we're dealing with extremely low densities, and so that means that different non-ideal effects come in to matter more. So give a sketch of the derivation and say something about which of the non-ideal terms, turns out there are 3 of them, matters in different regions of the disk. Okay, so that's sort of, if you like, specifying the problem from the point of view of how you would try to simulate it or study what's going on in different parts of the disk. And then just say a little bit about some numerical approaches and show some results of what people have obtained in that regime. So that'll be part 1, and then depending on how much time we have, so feel free to ask questions. We don't absolutely have to get through all this stuff. So if there's questions, do stop me. But if we do have time, we'll say something about this two-fluid dynamics. Say something about what the problem is there. Mention something about the fact that when we have 2 fluids which are interacting with each other, an interesting property is that can give rise to new instabilities which are not present in each of the individual fluids. So their coupling can if you like, destabilize the system. And again, we'll say something about some numerical approaches to that problem, and again, show just one result, basically, that comes up in that system. Okay, so let's start by discussing this question of non-ideal MHD, and let's start with the thing we've already discussed in this school, which is ideal MHD. Okay, so we have the induction equation here, and as was discussed yesterday, this represents physically a situation where the magnetic field, the magnetic flux, is perfectly frozen into the fluid. Okay, and so we can consider it in sort of 2 different limits if you want. You can imagine first that a magnetic field that is extremely weak, so it doesn't exert any significant back reaction on the fluid, and then the fluid is moving around however it pleases, and the magnetic field is being carried around, potentially tangled up by that fluid motion. Okay. You could also imagine a situation where the magnetic field is stronger, and then it will back react on the fluid through the momentum equation and the Lorentz force term in that, which was also discussed yesterday. Okay, so that's ideal MHD, and the first thing to note is, ideal MHD is always an approximation, of course, as was emphasized yesterday, and there's always more stuff on the right-hand side of this equation. And in general, in let's say many astrophysical systems, in principle, we sort of have to worry or should worry about the extra term, even if ideal MHD is itself a very good approximation. So if we're dealing with, let's say, a very well ionized system where the ideal MHD seems like a good thing. And the reason for that is that if the system particularly is turbulent, then it will be stirring around this magnetic field, and you'll get this sort of spaghetti-like structure to the magnetic field. And so very often that will both amplify the magnetic field, make it stronger, and it will also mean that the scale on which the magnetic field reverses direction tends to become smaller with time. Okay, so it's sort of like one of those stirring a coffee cup with some cream, and you get smaller and smaller structures as the mixing progresses. And so if you're in purely ideal MHD, that just continues. The magnetic field gets stronger, and it gets to smaller and smaller scales. But obviously, eventually, something breaks there, and that was what was being discussed a little bit yesterday in terms of reconnection and so forth, things that go beyond the ideal MHD approximation. Okay, so there's, particularly in many circumstances, but in disk circumstances as well, what happens on those small scales is interesting and raises some sort of interesting questions. So in well-ionized systems, the breakdown of ideal MHD is occurring on small scales due to things like formation of current sheets and so forth. And from a numerical point of view, that has the consequence that often we're dealing with circumstances where none of the dissipative effects that are present in the fluid, so due to the finite conductivity of the fluid or due to its viscosity, where none of those are properly resolved numerically. Okay? And so this is sort of an interesting difference between astrophysical fluids and in particular engineering fluids. If you sort of speak more within engineering type communities, people are very concerned about simulations where you do not have the correct Reynolds number, right? Where you're not really representing the true nature of the fluid. But in astrophysics, very often, very frequently, that's the case. If you think about something like the sun, dissipation scales are much smaller than any kind of numerical scale you can resolve. So you have to deal with that, and there are some interesting questions there, related to do the small scales in some way feedback on the large scales. So for example, if you consider, what's the ratio of the viscosity to the resistivity, that number can vary quite a lot depending on what the plasma properties are. And there's discussion about if you go to different regimes of that so-called Prandtl number, does that in fact affect the large scales of the flow as well as the small scales of the flow? Okay, so those are interesting questions. However, when we get to protoplanetary disk, we're dealing with a different situation, because the extra terms on the right-hand side are not just things that matter on small scales, they're actually things that matter on large scales. Okay, and so that's the unusual aspect, perhaps, of protoplanetary disks. It's non-ideal MHD, we have to worry about the non-ideal terms, and they're actually large in magnitude in many circumstances. And that comes about because the ionization level is low. So we can say just a little bit about the physics of the ionization. That's a complicated topic in its own right. And you can sort of think about two ways in which the gas in the disk might be ionized. So one reason it might be ionized is just that it's hot, and so it's collisionally ionized. And nowhere in the disk, at least in, let's say, low accretion rate systems, is the temperature going to get large enough to really significantly ionize hydrogen. Okay, so the bulk species in the disk is going to be neutral no matter what. But then there are other species which have lower ionization potentials, which will be ionized at lower temperature. Okay, so these are things like the alkali metals, like sodium and potassium. And so you get some ionization of those at temperatures that are more like 1,000 degrees Kelvin rather than the 10,000 degrees Kelvin you would think of for hydrogen. Okay. And on the left there's just an estimate of what sort of ionization degree you would get from those effects, making some assumption about the abundance of the alkali metals. And the point is just that you've got very low degrees of ionization from that sort of process. So you might be looking at 10 to the minus 13 at a temperature of about 1,000 Kelvin. So an overwhelmingly neutral system just from the point of view of thermal ionization. So that's at 1,000 degrees Kelvin. If you go out to where the Earth was forming, you might have temperatures of a few hundred degrees. if you go out to where Jupiter or Uranus and Neptune were forming, you might have temperatures below 100 degrees. So in that circumstance, the thermal ionization contribution is completely negligible. However, you also have non-thermal ionization from various sort of high-energy sources of radiation in the system. Okay, and there's various ones of those. So the star itself is going to be producing ultraviolet photons, so far ultraviolet photons for sure. It's going to be producing X-rays. Young stars are quite vigorous X-ray sources. And then there may be cosmic rays, which are in the environment, in the star-forming environment, which are coming in and impacting the disk. And all of those things will of course ionize the fluid. And even if you didn't have them, there are some short-lived radioactive species. Aluminum-26 is the most important, which will be decaying and producing high-energy particles, which can also cause some ionization. Okay. So you have all those ionizing sources, which will be, if you like, shining on the disk, in the case of the X-rays, the FUV, the cosmic rays, from outside, and they will be producing ionization. But the important point here is that even though those species have some penetration depth, it's generally small compared to the total column of the disk, at least relatively close to the star. So that's what's being shown on this plot. Here is the column density in grams per square centimeter, where you imagine this is the upper part of the disk, and then you're going to the right down towards the disk midplane. Okay? And at 1 AU, you might have a column density of 1,000 or a little bit more than 1,000 grams per square centimeter down to the midplane. And that will be enough to attenuate even cosmic rays, which are the blue curve in this case. Okay, so they will basically be wiped out exponentially because they have a stopping depth of order 100 grams per square centimeter. And X-rays, which are more securely known to be present in young stars and also have a high luminosity, those have a shorter penetration depth, and so those get cut off exponentially even stronger. So that's the ionization story. If you want to know what the ionization fraction is, you also have to worry about the recombination, which is a whole different story. But the bottom line is that you end up with very small ionization degrees. So 10 to the minus 13, less than 10 to the minus 13, let's say in the terrestrial planet-forming region of the protoplanetary disk. So the question is, what does that do to you? So in terms of the physics, it's sort of relatively straightforward. So here we imagine we have a magnetic field, and we now have a plasma, if you like, in that magnetic field, but the ionized contribution is actually very, very small compared to the neutral contribution. So we have negative charge carriers, positive charge carriers, and neutrals in that system. And so saying the neutrals outweigh the charges by 10 to the 12, 10 to the 13, 10 to the 14, or some number like that. Now, if we just think about the electrons and the ions, they interact with the magnetic field just in the same way that they would in ideal MHD. Okay, so those are tied to the magnetic field. We can think about them as gyrating around these field lines. The neutrals, on their own, of course, don't care anything at all about the magnetic field. So the circumstances we have, most of the mass, in principle, doesn't care about the magnetic field directly, but the charge component does. And so I've tried to illustrate here, in these kind of systems, the negative and the positive charge carriers are not equivalent, right? So we're not dealing with electrons and positrons for sure here. We're dealing with negative charge carriers that may be electrons, free electrons in the gas. The positive charges may be positively charged molecules, for example. So much, much heavier species than the electrons. Okay, so then we can then imagine, applying an electric field to this system and asking what will happen. We could even consider not even having an electric field. And so if we put a field there, the charged particles will tend to want to drift. Negative charges in one direction, the positive charges in another. And if those charges collide with the neutrals, then those collisions will provide some coupling between, if you like, these separate fluids in the system. Okay. So that's what's going on. We've got neutral fluid and a charged fluid. They have different sort of basic interactions, but they're coupled due to the fact that they collide with each other. And where it gets sort of complicated or interesting is that how that works depends on the density and therefore on the rate of these collisions. And you can sort of imagine three different regimes. So one is at relatively high density, where you've got these charged particles, they're trying to drift, but they're colliding very, very frequently with the neutrals. Okay? So that's a high density regime, and in that case, the drift speed is going to be completely limited by these collisions. Okay? So in that case, if you like, things are actually quite well coupled together, but the collisions will tend to dissipate the current itself. Okay? So that's the regime of ohmic diffusion. Okay? So in sort of a big picture where you're thinking of non-ideal MHD, if you're dealing with high density systems or thinking about the breakdown of MHD in other systems, ohmic diffusion is often the first thing you think about. Now you can also imagine a situation of very, very low density. Okay? So you have very, very low density, the electrons and the ions are tied to the magnetic field, and they're almost independent of the neutrals completely. If you go to low enough densities, you could really imagine that the charged particles are interacting with the magnetic field in their own way, and the neutrals are just sort of sitting there not really caring about what's going on at all. If you go to slightly higher densities, there is some coupling, but there can be drift, or there will be drift, between the charged species and the neutral species. And that's the regime we describe as ambipolar diffusion, which is the main effect that people mainly discuss in the context of star formation. And then there's an intermediate regime, which occurs because in this system, the ions and the electrons are not equivalent, where you can have one of the species tied to the magnetic field, and the other not so much. Okay? And so that comes in at some intermediate densities, and that's related to the Hall effect. So that's the physical situation. And I should say, I think this is a reasonably straightforward physical picture. How this gives rise to the actual non-ideal terms is not something that I ever find very intuitive. So I'm going to explain sort of mathematically or physically where it comes from, but sort of tying it to this picture of how well things are coupled to the field and so forth is something that I don't think is completely easy. Okay, so how are we gonna do this? Okay, so we want to do something that's MHD-like. Okay, and as was sort of said yesterday, MHD is actually, when you sort of think about it, involves like a little bit of magic or surprise. Okay, because when you think about MHD, just ideal MHD, we're thinking about plasma systems, and we're thinking about currents, right? So when you are introduced to magnetic fields and electromagnetism, it's all about currents and how those source magnetic fields, about wires, magnetic fields going through the wires, all this kind of thing. But in the MHD description of things, a lot of that doesn't really appear explicitly in the equations. So it's a plasma system, so we definitely have at least two species, ions and electrons, or positive and negative charges, but we describe that in terms of just one fluid. Okay, so we've managed to write a single fluid description of something that seems like a two-fluid system, or is a two-fluid system. And then we write it entirely in terms of the magnetic field, and if we don't want to care about the current, we can proceed without really even knowing that the current or the current density actually exists. Okay, so these are just properties of regular MHD. So in going to the non-ideal MHD equations, the sort of general strategy for how we get to those equations is to sort of preserve those good features of MHD, or that same spirit of the approximation. So in particular, the way we, if you like, get to the non-ideal MHD equations is to start by thinking explicitly about having multiple fluids, positive charges, negative charges, and neutrals. And we can start by writing explicitly the momentum equation for those different species, which are coupled together by collisions. And so that's sort of physically what's going on, and that was the physical picture that I had on that previous slide. And the key is we can then reduce that to a single fluid description in the same way as we do for ideal MHD. Okay, so we don't, in most cases, have to consider individual species separately. And then we can do basically the same thing in ideal MHD. We made use of an Ohm's law and Faraday's law. So a relationship between the electric field and the current, and then a relationship between the electric field and the rate of change of the magnetic field. That's how we got to the induction equation yesterday. And so what we want to do here is to derive basically the same sort of thing, but with a more complicated relationship between the electric field and the current. Okay, so that's basically how it goes. That's at the top level, the strategy for how we get the non-ideal terms. So if you want to really read about how this is done in all detail with the steps laid out, Steve Balbus, I think, has a nice description of how you get to the non-ideal equations, and it's in this. It's actually, I think, it's a conference proceedings from some number of years ago, which really goes through it all in quite a lot of detail. So it's called magnetohydrodynamics of protostellar disks. You can find that on the archive. So it's one of these circumstances where the big picture of how this is done, I think, is fairly straightforward. I already mentioned that, and we'll say a little bit more about it. The actual details of the derivation, I would say, are, depending on how you look at it, delicate or messy. Involves, a number of approximations which have to be carefully justified at each step, and Steve goes through those in that review. So that's interesting if you want to see exactly how it's done. It does mean that, in principle, one should, I think, take care if you're dealing with non-ideal MHD situations which are somewhat removed from those that are typically considered, because there are various approximations in the derivation, and in principle, one could get into circumstances where those approximations, which in the normal circumstances are valid, turn out to be not valid anymore. Okay, so that's just a word of caution. Okay, so how do we get to the non-ideal equation? So there's sort of two equations we need to get to. We need to get to a momentum equation, and we need to get to an induction equation. So if we start by thinking about the momentum equation, the basic argument is related to timescales of different phenomena. Okay. So we can start with just writing things down explicitly. Imagine we have 3 momentum equations, one for the neutral part of the fluid, one for the electrons, and one for the ions. Okay. So these are basically all the same. So we have the terms on the left-hand side as usual. We have pressure gradients. Here we have gravitational forces. So imagine we have a disk, but think about the stellar gravity there. And then on the far part of the right-hand side, we have some extra terms. So we have these terms, Pni, Pne, and then their symmetric counterparts, which represent momentum coupling due to collisions between these different species. Okay? And you can see here in the neutrals, we have a contribution from the ions, a contribution from the electrons. We then have the other terms in the electron and the ion equations, and we assume we're dealing here with weak ionization, so we don't worry at the moment about collisions between the ions and the electrons. Okay. So for the neutrals, we just have these momentum terms, but for the charged species, we also have these electromagnetic terms, okay, which are the same sorts of things we had before. So Ne here is the number density of electrons, Ni is the number density of ions, and then Z is the charge that we have on the ions. So in writing that, we've not made any particular approximations, but you can see it's a messy system, or it's got a lot of complexity. And then the basic idea to make things simpler is to note, if we imagine, let's say, the dynamics of the ions here, we have a bunch of terms which sort of represent the macroscopic evolution of this ion fluid. Okay, so terms on the left-hand side, the pressure gradient, the gravitational force. Yeah, so these are actually still quite high density systems. So we should be, generally, we should be all right in that sense. So even though, yeah, for example, we talk about ambipolar diffusion and we talk about low densities, but in disks at least, these are still densities that are very high compared to, like, say, IgM type densities. So those are sort of circumstances that might be might have more worry about those actually in more high energy circumstances like galaxy clusters and things like that. Yeah, so these terms on the left and the first couple on the right represent sort of macroscopic fluid evolution scales. But these ones here represent faster timescales, stronger terms. Okay, so the idea here is to say, well, okay, if the two terms on the right hand side, the Lorentz force one and the momentum coupling terms, if those are really much larger than the other terms, then we can just say that for some purposes, we can just consider those terms and say that all the stuff to the left of those is representing much longer timescales and is a negligible effect. Okay. So if we can do that, then we can actually say, we can just ignore all of this complicated stuff and just say that this is equal to 0. Okay. So we can get some relationship between the momentum coupling term and then this one representing the electromagnetic effects. So it's going to be based on, basically actually related to the question we had before, related to the density, right? How often, if you like, is a particle going to be colliding with something else compared to like the macroscopic evolution time of the system? Okay, and so of course we can always find situations where that would not be true, but in some appropriate limit, we can make interesting limit. These terms are going to be large compared to the other ones. Well, that would depend, in principle, obviously, on the system. So it'd be something like, so for example, if you look at that gravitational term, right, that's going to be representing the orbital motion around the star. So that will be related to the orbital period, right? Obviously, we could, it's not so easy to make an instant discussion of, say, how big the pressure gradient could be, right? But those kind of arguments would give you those terms. Okay, so we can do the same argument for the electrons. Okay, and then so if we just look back at those equations briefly, so here's the ion part, here's the electron part. So we're going to do the same thing for the electrons. Okay, so we're going to ignore all this stuff to the left, and then we're going to get two equations, both of which involve the electric field here. Okay, so this one, and then the same one for the electrons. So we can eliminate the electric field between those two equations. And we also need to assume charge neutrality, overall charge neutrality. And then if we do that, we can write down an expression for what the sum of the ion neutral and the electron neutral collision terms is. And it has this rather simple form on the right here. Okay. And then we can observe that here we've got the difference in the velocity between the ions and the electrons. And this is related to the current density in the fluid. Okay, so if we imagine that say that the ions were completely at rest, so they had VI equals 0, then the current would be due to the velocity of the electrons on its own. Okay. So here's the current density. So we can then replace VI minus VE with this, and then we can substitute that back in the first momentum equation, and we get this expression. So we get a momentum equation that it just involves V. And this is the same as we had in ideal MHD. Okay. So we have pressure gradient, gravitational piece, a magnetic piece, which is basically J cross B on the right-hand side. Okay. So that's gotten us to the momentum equation, and we've gotten there without ever having to say anything really about exactly what this coupling between the different species actually was. Right? The whole point here is that we basically sort of managed to eliminate that. Okay, but there were as we've as the questions were emphasizing, there were some assumptions there, right? Because we obviously had to do some things to ignore those other terms, right? And those hold in some regime, but not necessarily in every regime. Okay, so that's relatively straightforward. Okay, now if we now want to get the induction equation, so we want to get the equation for the time rate of change of the magnetic field itself. And to do this, this is not so it's not so physics independent, right? Because the whole point of non-ideal MHD is that it is involving these collisions between the different species, and the fact that some of the collisions are more important than other collisions, and so forth, that the species are not all equivalent. So we can't go to get the induction equation. We can't hope for sort of complete generality, if you like. We have to get more into the weeds of the actual physics of the collisions and how large the different terms are actually going to be. Okay. So we can just sort of say in principle, though, how we get going. What we say is, let's say, imagine how much momentum transfer we have between the neutrals and the electrons. Okay. So how many collisions are we getting, and how much momentum is being transferred there? So it's going to obviously depend on the velocity difference, so the velocity between the neutral species and the electron fluid. It's going to depend on the collision frequency, which I'm writing as nu here, on the number density, and on the reduced mass for how much momentum we get when we get a collision. So we can write the different collision terms in this form, and then you can sort of go to your textbook on how you calculate collision rates and collision outcomes, and for a particular fluid, derive an explicit expression for how strong, say, or how large the collision frequency actually is for one species colliding with another. Okay, so that's the sort of thing people have done. So how do we use this? Well, we can go back to the electron momentum equation. So here we did this for the ions, okay? But we could do the same thing for the electrons. We already mentioned that. So we can cross off these terms up to here and just consider these last two on the right-hand side. So we've got this minus that equals 0. So that's what we have there. Okay, and then we can substitute for the collision terms here. Okay, and so here we've made a substitution because the reduced mass becomes basically the electron mass when we're considering very different masses. So that's what we have, and that's sort of close to the sort of thing we might like, right? So here we have this equation. This is V cross B over C, okay? And if the electron velocity was just the overall velocity, the single fluid velocity, this would be the ideal ideal MHD inductive piece. Okay, and here we have VE minus V, and if that was not V but was VI, then we would have something that would be the current, or the current density. Okay, so we're sort of making that even at this immediate stage, this first substitution, we've gotten to something that is sort of getting towards a more complicated version of Ohm's law that we could use to derive the induction equation. Okay. Okay, so this is the point where we pause and sweep everything under the carpet and say, read Steve Balbus's article or trust me or whatever, This is not yet what we need to produce the non-ideal induction equation. So there's various things that we have to do at this point, okay, which are the things I'm not going to go through. So there's some algebraic steps. Okay, so actually the first thing we do here is we say, let's make this VE minus VI, and then add on the term that we've just removed. Okay, so first thing we actually do is we just expand this out into terms, some of which do directly involve the current, but then have some extra things left over. So there's a bunch of just algebraic manipulations of that kind. But then we actually have to use some physics to assess which of the terms are negligible and which are not. Okay, and that's the part that, as I said, is requires a little bit of thinking in order to convince yourself that it's correct. And then finally, this is astrophysics. So as often happens, we have to suffer some confusion because the notation that's used for the different non-ideal terms sometimes sort of feels deliberately confusing, right? So we're basically, when we talk about collisions, we're just talking about the collision frequency between different species, but people use different terms to express those same concepts. Okay, but you can do that, and what you end up with is this expression. Okay, so you end up with a relationship between the electric field and then the magnetic field, and the current density, which is just the curl of the magnetic field. And it has 4 pieces. It has an ideal piece, it has an ohmic piece, a Hall term, and a term representing ambipolar diffusion. And the quantities that are entering here are sigma, which is the conductivity of the gas, Ne, which is the number density of electrons, and then for the ambipolar part, rho is the density of the fluid, rho I is the mass density of the ions, and then this gamma here is a quantity called the drag coefficient, which is just another way of expressing the collision rate between these species. And then when we've got that, we can go back to Faraday's law and straight away get the non-ideal induction equation, which then takes this form here. Okay, so in ideal MHD, we just have this first piece here, but now we have 3 extra terms coming in on the right-hand side. Okay. Here, eta is the magnetic resistivity, which is just inversely proportional to the conductivity. Okay, so that's ohmic, this is Hall, and that's ambipolar. Okay, so that's the answer here. Okay, that's the non-ideal induction equation, and hopefully you've got some sense of how we derived it, even though we didn't certainly go through the messy details. I would say no. So what you need here is you need to get to this. You just need a relationship between how much electric field you have and how much current is produced. Okay, and so what you're the physics part you're interested in is how that is modified by having these collisions. Okay, so that's really this term on the top is actually sort of the thing you're trying to derive so that you can get to the induction equation. So you're basically looking for what those extra terms, what the mathematical form of those extra terms is. Okay, so there's various things you can say about this. Okay, so the first thing to note is if you look at the non-ideal pieces, they involve the ionization degree as they should. Okay, so the resistivity here, eta, is inversely proportional to the electron fraction. Okay, this here you can see the electron number density is explicitly appearing on the bottom, and then for the ambipolar part, the ion density is also appearing on the bottom. Okay, so all 3 of those depend on the ionization degree in basically the same way. And clearly, the absolute strength of those non-ideal terms depends, if you like, entirely on how ionized or poorly ionized the fluid is. And if we make things more and more weakly ionized, they just become stronger. Yeah, the current is still here, just curl B. So yeah, the ambipolar part in particular, if you then write that as curl B, you've ended up with a bit of a mess, right? You've got curl B, cross B, cross B. Okay, so you need to think about what that really means, or maybe don't worry about what that means. So the absolute strength depends on the ionization degree, and so there's sort of a whole game in protoplanetary disks of trying to calculate the ionization degree accurately. Okay, and that's difficult. It will depend on the problem. So I'm going to sort of say a little bit more about that in a moment. But in general, you would need to ask, what ideal MHD effect are you interested in? And then how much you'd have to wind up these other terms before you made a significant influence on it. And so that would depend on what circumstance you were thinking about. So it wouldn't be a general statement, this is ideal and this is non-ideal. It's a more nuanced question. Yes, yeah. So definitely it will depend on the scale. Yeah. So in particular, like the ohmic piece here is clearly a diffusion operator, and so that will be important on small scales. But if there's a large scale magnetic flux, that still is going to be a conserved quantity, and it's not going to be very easy to get rid of. Okay, so that's the absolute strength, and that depends on this question of the ionization degree, and so that involves a lot of chemistry to try to calculate. It involves worrying about what the dust size distribution is, and many messy things like that. Something you can say, however, is you can ask, well, which of the three terms on the right is more important than the others? Okay, and there's some sort of basic things you can say there. You can think about the density, and you can see that the density, or a density at least, enters on the bottom in the Hall term, doesn't appear in the ohmic term, and then in the amber polar term, you've actually got two terms that involve the density on the bottom. So as you go to lower density, you go from ohmic to Hall to amber polar as becoming increasingly more important, and that matches the sort of the cartoon version of the physics that I gave right at the start. Now you can also see that, say, if you look at the amber polar piece, so that's called amber polar diffusion, okay? But if you actually look here, we've got three things that involve the magnetic field. We've got two B's here, and then J is curl B, okay? So if you think about that in terms of a diffusion, that would say you've got a diffusion coefficient, which goes as B squared, okay? So how important amber polar diffusion is depends itself on the strength of the magnetic field that is involved. And as you go to stronger magnetic fields, it becomes stronger. And then, not visible really in the equation, but there's also some temperature dependence, because the resistivity, the amber polar drag coefficient, those are coming from collisions, and collision rates in general have some temperature dependence. So there's mostly a density dependence or a strong density dependence. There's some temperature dependence. For amber polar diffusion in particular, there's a strong B dependence. Okay, so you can consider that in different environments. If you do it for protoplanetary disks, a simple thing you can do is you can take ratios of two of these terms. So you can take the ohmic term and divide it by the Hall term, and just ask, given some particular scale, so coming back to the question earlier, given some particular scale, which of those would matter the most? Okay. And here's the sort of thing you get when you do that. So here's a plane of density and temperature. So we're talking about low temperatures here, and a very wide range of densities. Okay. And what's shown here in the different sort of shaded regions are different orderings, different estimated orderings of these non-ideal effects. So over on the right here, high densities, the ohmic term matters the most, then the Hall term, then the amber polar term. Okay. And these lines here are just simple estimated tracks of what the density-temperature relation would be in the protoplanetary disk at the midplane, and then up in the atmosphere where the density is much lower. Yes, this does have to assume a magnetic field strength, and so this is assuming, I think, a magnetic field that would be a Shakura-Tsarnaev alpha of 10 to the minus 2. But you do have to make an assumption about that. So yeah, so this is right. Remember we said that the amber polar part, all these terms in general, but they do depend on the magnetic field. Okay, so if you make the magnetic field much weaker, then you change the ordering of the terms. So really, one should be making a sort of three-dimensional diagram here where you have temperature density, and then you have a third axis of magnetic field strength. But here some assumption has been made about what the magnetic field strength actually is. And so what you find here generically is that, as you go from close to the star, so there's a tenth of an AU out to far out, you track across different regions where this ordering is different. And if you go from the midplane of the disk up to the atmosphere, of course, the density becomes much, much lower because it's dropping as something like a Gaussian. And so eventually you get into an amber polar dominated regime there. So if you go to Steve's article on this, he gets to this non-ideal induction equation, and then says it's only natural the reader should be taken aback by the sight of this equation. In the sense, I think that it's not looking very nice. Be assured that it's rarely needed in full generality. Okay, so that's sort of encouraging words. Protoplanetary disks are one of those circumstances where, unfortunately, it's often necessary, maybe not to consider all of these terms at once, but generally to consider more than one. Okay, and the reason for that, as I was just saying, is suppose we're at 1 AU. Well, in the midplane of the disk, you would say the Hall effect is the most important, followed by ohmic diffusion, and amber polar diffusion would actually be quite weak in that circumstance, right? So there's a reasonably strong ordering. But then if you just go up in the disk, from the midplane up to the atmosphere, you follow this red arrow, and eventually you get to the point where amber polar diffusion becomes the dominant effect. So if you're sort of interested in what the structure is like at 1 AU, you've got regions in close proximity where these different effects matter. So the seed magnetic field here would come from the magnetic field of the star-forming cloud that formed the star and the disk in the first place. And so how strong that is a whole different question. But if you just take the magnetic flux that would be present and imagine collapsing it down to these scales, you would probably actually get a magnetic field that perhaps is a little bit too strong, and for example, would perhaps remove quite a lot of the angular momentum from the fluid. That's the so-called question about magnetic braking in star formation. So we don't think probably that these disks have such strong net magnetic fields, but it's very likely they have some magnetic field that's left over from that purpose. Yeah, so we don't need to build the field up from scratch. I think I'm going to defer that to someone else later in the week to answer. They obviously play a role, but that's a complicated question. Okay, so yeah, so this vertical slice of the disk includes these places where different things dominate. So that's a complication for disk studies. Okay, but we can say some things about how this works. So one thing we can ask is, well, what effects might these terms have on disk evolution? So going back to this idea of protoplanetary disks as accretion disks, how is gas accreting through the disk and reaching the star? And there's a simple argument we can make, which is to compare the first two of these terms. You can see the first two of them are easier than the other two, so it's good to start with the easy things. So if we just had the induction part, so we just had ideal MHD, then if you're in a disk environment, you're unstable to the magnetorotational instability, which I think we'll be hearing about after the break. So here's a little simulation of the magnetorotational instability in ideal MHD. So this would be the radial direction, vertical direction, the azimuthal direction. This is a little shearing patch of the disk. This is the density, and it produces this turbulent box of fluid here. In this specific case, there was no net magnetic field, but there can be. Okay? And it makes a difference whether there is or not. I'm pretty sure that this one, the movie is being shown, was initialized with basically mostly a toroidal field, which had no net vertical component and was not conserved. Okay, so that gives you the magnetorotational instability. So you can ask, coming back to this question of whether it's ideal MHD or non-ideal MHD, you can ask how much effect would, say, the ohmic term have on that effect, right? So suppose our interest is the MRI, okay? Is that going to be affected? So you could make a timescale argument here. If you just consider this ideal MHD, that gives rise to an instability. It has some characteristic timescale. So here we have h, which is the vertical thickness. VA is the alphane speed. And if we just consider this ohmic term, okay, so that's a diffusion-like term. So it has a diffusion timescale, which is something like h squared over the resistivity, okay, on a scale of h. So we say that the relevant thickness is the thickness of the disk. The relevant scale is the thickness of the disk. So from a point of view of an approximate argument, we can just say the non-ideal term, which is the ohmic one we're considering here, will become important if this timescale becomes short compared to this timescale. So the critical situation is when they're equal. So we set these timescales equal, and that amounts to a condition then on the resistivity, which is just h times VA. Okay? Another way of saying that would be that's something about the magnetic Reynolds number where the system would matter. And if we know something about, or if we calculate how this critical resistivity is related to the electron fraction, then this amounts to a critical electron fraction where on one side, if we're ionized enough, we're sort of more like ideal MHD. If we're too weakly ionized, we're more like, we're just damping everything away, in this case by the ohmic term. And this is an argument that dates back to Charles, now a few years ago. And the striking thing is that the critical number is, well, the first thing to say is the critical number is very low. Okay, so it's something like 10 to the minus 13. It will vary depending on where you are in the disk and so forth. But it's a very, very small ionization degree. So in terms of sort of one way of thinking about that is that saying, well, like ideal MHD in this circumstance is still an interesting approximation, even down to things that are way below what we would normally consider to be an ionized fluid, right? So 10 to the minus 8 is a very, very neutral fluid, but that would be orders of magnitude above this threshold. So it's a very low level, but as we also saw, or at least stated, the actual ionization levels can be even below that level. So if that's the case, then the ohmic term you would predict would damp the MRI in protoplanetary disks. And in the regions where that ohmic term is important, which would be fairly close to the star, it would reduce or suppress the effects of MHD turbulence in that region. Okay? And that gives rise to this concept of the dead zone, where at some points in the disk, maybe the turbulence has been really wound down by the non-ideal terms. Okay, so that's the ohmic part, but then there's also these other terms, okay, the Hall term and the ambipolar term. And those are much harder to say something really simple about, part, as you can see there, because they have a significantly more complicated mathematical form. So in general, the ambipolar term does give rise to damping, but as we've emphasized, it depends on the strength of the magnetic field itself. Okay, so it's a B-dependent damping. And this should be 30 AU. The sort of region of the disk for typical disk models where you worry about this is in the outer part, so 30 to 100 AU, those kind of scales. So if you think actually about those ALMA images of protoplanetary disks that we started with, those are images of the disk on those kind of scales. So when you're looking at that, you should really be thinking about, if you think about MHD effects, you should be thinking about MHD effects that are strongly modified by ambipolar diffusion. And then the Hall part is trickier again, because unlike the other terms here, this has actually a dependence on the sign of the magnetic field in addition to the strength of the magnetic field. Okay, so it gives rise to dynamics that depends on how the magnetic field is oriented with respect to some other characteristic direction in the system, for example, the rotation, the axis defined by the rotation. So that can give rise to other instabilities which are different from the MRI itself. And some of those can give rise to laminar MHD stresses, so angular momentum transport that occurs because of ordered magnetic fields in the fluid, but not small-scale turbulent magnetic fields. So it's a complicated story. So you could write this, one way you can write this is you could write this, okay, so here we've got an eta for the ohmic term. If you wanted to write the amber polar diffusion term in a something similar, you could write it as like eta A times curl B, right? And then you'd pick up, in eta, you would pick up 2 factors of B. Yeah. And of course, one should say that the amber polar term, as you can see there, is not just a simple diffusion like the ohmic thing. So it has a different character as well as that, but just in terms of a simple simple way of thinking about it, it has that B squared. So here's just some pictures from fairly recent calculations of protoplanetary disks with non-ideal MHD. This is Hu et al., Bethune et al. So this is looking down on a disk, and this is a model that includes actually quite a lot of chemistry. So it attempts to calculate the actual magnitude, the actual physical magnitude of these non-ideal terms quite accurately. Here's a model with less complicated chemistry. You can see this has a net field threading it. So the white lines here are the magnetic field. And I think, what you could basically say is that, these non-ideal terms in the MHD limit at least have, as expected, a dominant impact on MHD turbulence. And there's a lot of interest in the idea that you can maybe generate large-scale disk structure out of some physics that's related to these non-ideal terms. You can sort of see that in this calculation. You can sort of see that the vertical field, the net field, is getting bunched up in some regions and spread out in some other regions. So you can imagine that could give rise to a ring-like structure. And then that's actually explicitly what's being shown on this image to the left. Though here there's, as I say, not just non-ideal terms, there's also some chemistry being taken into account. So there's actually some other physics taking place there. Okay, so a lot of things there, not fully understood by any means. Okay, I would say if you go back to those ALMA images, those may be showing planets, but they may also be showing in some cases phenomena that are sort of associated with this kind of physics. We don't know. This is showing gas density. So the strongest thing you're seeing here is actually a snow line effect. So it's not an MHD effect, but there are the weaker stuff is MHD. Okay, just then one slide on numerical aspects. Okay, so if we're dealing with non-ideal MHD, and these non-ideal MHD terms are really important, then how those are treated is obviously also correspondingly important. And there's different ways that this has been done, in the literature. And so one issue is that the time scale associated, if these ohmic terms and the amber polar term, if those are really strong, then the time scale that can be associated with those terms can be very short. Okay, so it can be much shorter than the time step you would need for ideal MHD. So people have done that in various ways. There's an approach called super time stepping, which amounts to taking substeps of a large time step, but not evenly chosen substeps that are ordered in a particular way, so that you can do that more efficiently. And that's one way that people have used to look at those terms. So the momentum equation is still basically fine. Yeah. So yeah. Well, you're still obviously preserving div b equals 0. So you still have that same. Basically, you have the same issues, I would say, as for ideal MHD. And the Hall term is difficult as well. Okay, and the reason it's difficult is that that has quite difficult high frequency behavior. So that in general needs to be sort of cut off in some hopefully physical way. And people have done that in a whole variety of different ways. So there is some work in using spectral approaches. That's for incompressible fluids. Okay, it's been done for incompressible fluids at least. It's been done in an operator split approach, which would be maybe the simplest approach you might imagine. Often they're needing to add an artificial resistivity of some kind to stabilize things. And it's been done by modifying the flux in the Riemann solver. So there's a variety of methods. Well, in principle, it could be done for compressible. The work, the papers that have been published so far have done it in the incompressible regime. Okay, so that was what I wanted to say about MHD. So now let me say just briefly 15 minutes on the other topic of two fluids. So when you look at these disks, we're looking at least in this image, you're looking at the dust itself, at the solids, right? So small particles which are aerodynamically coupled to the gas. So we'd like to ask, how does that coupling work, and what does that give us for disks? So maybe the way to start with this is to think about just a single particle, which can be of some arbitrary size, which is moving with respect to the fluid around it. Okay, how does that interaction work? And I think if you sort of think about this, the thing that would sort of spring to mind are terrestrial examples of this kind of interaction, where really it's an interaction between it's a hydrodynamic interaction between the particle and the surrounding gas. So here's a nice image from an old book of fluid dynamics examples, where you have a cylinder moving through a fluid at some moderately high Reynolds number. Okay, and the fluid flows past, and it has some turbulent properties and so forth. However, in protoplanetary disks, this is normally not the regime you're interested in until you really start thinking about really big objects. Okay, so for smaller objects, certainly things that are, say, millimeters or smaller than millimeters in size, the particle size is actually smaller than the mean free path of the gas molecules in the disk. So it doesn't work like this fluid situation, because on the scale of the particle, the fluid is not actually a fluid at all. It's just molecules bouncing around. So instead, it's in this regime described as Epstein drag. Here's an expression for it. So rho is the density of the fluid, S is the size of the particle, VTH is the thermal speed in the gas. And the key point is that the drag force is linear in the velocity difference between the particle and the gas, rather than being quadratic, which is the sort of situation you normally associate with. So if you're a cyclist having to worry about drag in going faster, it would be great to be in the Epstein regime of drag, right? Because if you doubled your speed, you'd only get twice as much drag rather than 4 times as much. Might not be so good if you had to breathe as well, because the density would be some tiny low value. So in this Epstein regime, you can characterize the interaction sort of pretty fully in terms of this quantity called the stopping time. So suppose you have a particle moving delta V with mass m relative to the gas, so its momentum in that relative motion is m delta V. Divide that by the drag force, you get a time scale. And what's nice here is that in this regime, the delta V just cancels out. So this stopping time, Ts, is really just a property of the particle, not how fast it's moving relative to the gas. And you can often make that dimensionless by multiplying it by a characteristic frequency, and often in disks, you multiply by the Keplerian orbital frequency, omega k. And then it's called the dimensionless stopping time, or the Stokes number. The Stokes number can also be used to refer to many other things. So if we think about single particles, there's actually a lot of interesting things to do with just single particles, which I'll briefly just mention a couple. One is that if we just have individual particles, their interaction with the gas disk tends to lead them to move inwards towards the star. And you can think about that in sort of 2 ways. Imagine the gas disk. It's basically in a situation where the inward force of gravity is balanced by rotation, but there's also a little bit of a pressure gradient in the gas, which generally, if the pressure is high close to the star and low far out, means that the gas is moving at a slightly sub-Keplerian rate, orbiting a little bit slower than Keplerian. So if you imagined a large object that's moving at the Keplerian speed, it would feel a headwind due to that sub-Keplerian gas. So then that would give a drag. It would spiral towards the star. If, on the other hand, you imagine a very small particle that's being carried around with the gas in the disk, it's being carried around, but it doesn't feel the pressure gradient, so it's orbiting at too slow a speed compared to what the balance of forces would suggest. So that very small particle would be being carried around with the gas at the sub-Keplerian speed, but then it would have a terminal velocity, basically, drift towards the star. And so this gives rise to radial drift, which can occur on a very short time scale. So here's this dimensionless stopping time. Here's the drift speed in orbital periods. it can be as fast as 1,000 orbital periods, so 1,000 years at 1 AU. So solid material can move around in the disk very, very easily. And then another interesting possibility is, suppose you have some more interesting fluid structure in the disk, like a vortex. If that's a high-pressure vortex, basically the same sort of physics works. The high-pressure vortex will tend to attract solid material in some appropriate regime of aerodynamically coupled size, and that solid material will start to build up in the core of the vortex. Whether that's something that we are seeing in disks is an interesting question. Okay, so go back to these ALMA images. I would say there's those simple effects, which really just rely on the gas having some particular structure, and then the solids responding to that gas structure. This is sort of probably what we are basically seeing in some of these images. So in particular, when you see these rings, no matter how these rings formed, probably they are reflecting the fact that the particles are moving around in the gas, and the regions where you see the bright emission is where the velocity is slower, and therefore the particles are piling up. Okay, so we may well be seeing that sort of single particle interaction between the gas directly in these images. And then here you have a system where there's a big asymmetry in the emission on one side, significant asymmetry. A popular interpretation is that when you see things like this, perhaps this is actually reflecting a vortex-like structure in the gas, which again is concentrating particles in that region. Okay. So, for a lot of observational points of view, already just having just particles that are responding passively to the gas is already a very interesting thing. However, there are other interesting things that occur when we think explicitly about fully coupled two fluid systems, where we don't just worry about how the particles respond to the gas, but how the gas responds to the particles. Okay? And so what we're thinking about then is a system where we have drag on the solids and a non-negligible amount of back reaction from the solids onto the gas. So you can consider this in various limits, and I'll just mention one which is important from a sort of analytic point of view. A simple limit where you consider that the gas is incompressible and the dust or the particles are represented as a fluid, but a fluid that does not have pressure, okay, because they're really just solid particles, not a gas. So in that case, you can sort of dispense with the continuity equation for the gas, just say that the gas has no divergence, and you have a continuity equation for the density of the particle fluid, which is rho p. Okay. And then you have momentum equations for the two species, for the particles, for the gas, which have some similarities, but the gas one has a pressure gradient, which the particle one does not, of course, and then they're coupled by terms that depend on the velocity difference between the particle fluid and the gas fluid. Okay? So this is, in some sense, of course, a little bit similar to what we were talking about for MHD, non-ideal MHD, except here the coupling is an aerodynamic coupling rather than collisions between the microscopic particles. Okay, so this is one limit. It's obviously not the only limit you could consider for this kind of coupling. But in the disk circumstance, this one is particularly interesting because you can analyze the linear stability of an equilibrium of radially drifting solids within this approximation. Okay, so the state you're considering is an unstratified gas disk, so no vertical variation in density. You have gas, you have solids within that gas, and the background state has the gas moving at a different speed, orbital speed, than the solids. So there's a drag force, and that causes the solids to move globally inwards through the gas. To conserve angular momentum, the gas must be moving outwards as the solids move inwards. Okay, so that's a well-defined equilibrium state, and you can study its stability. And it was found now 15 years ago almost that situation is linearly unstable. And that's known as the streaming instability in this context of protoplanetary disk dynamics. And these are just some images from the original paper by Udin and Goodman. So here you've got the relative density of the particles relative to the gas. Here you've got the stopping time of the particles, Stokes number as we defined before, over a few orders of magnitude in size. And then these contours are contours of growth rate of this linear instability. And for many circumstances in disks, it's not an extremely rapidly growing instability, so it's often quite a lot slower than the dynamical time. But it's present, as you can see here, in quite a broad range of these critical control parameters. So something we'd like to know is, how does that kind of instability operate in disks? What happens to it in the nonlinear evolution of the instability? So how can you do this? Well, so this can be represented in different ways, which I'll just sort of briefly touch on. So one idea, which is really the closest to the analytic description, would really be to imagine that the particles and the gas are really both fluids. Okay? And the difference is simply that the particles are a pressureless fluid. Okay? So that's one idea, and that could be extended to not just consider a couple of fluids, two fluids, but to consider perhaps many fluids where the different particle fluids represent different sizes of particles. Because different size particles will respond in different ways to these coupling situations. Okay? So that's something that's been done, and you can find an implementation of that in the Fargo 3D code, and this is a paper for it. And so here's just a sort of schematic of it. You have continuity equations for the different species, and then the velocity, the momentum equations have some coupling term, which here has just been written as F sub I, okay, which represents the momentum coupling between the different fluids. So this has some nice properties. Here you obviously get the same resolution for each fluid if this is done as a grid-based method. Each of the fluids is represented in an equivalent way on the grid. And this is actually the closest to the analytic setup where this streaming instability that I was discussing a moment ago was derived. So it's not quite the same because normally here, or often here, you don't have an incompressible gas fluid, but you could have an incompressible gas fluid. Now, often, or in the regime where this is valid, this force due to the coupling is rather strong. Okay, so you probably need an implicit treatment for that collision term because the explicit time step would be very short. And a property here is obviously that if you're representing everything as a fluid, then at each grid point, there is one value for the velocity. The velocity field is single valued as it has to be for a fluid. But this is one way in which you can study things like the streaming instability and other possible instabilities that involve multiple fluids interacting with each other in the disk. Now there's a weakness to that kind of approach, which is if we go from small particles, so very small particles are really very well coupled to the gas. Okay, so they will have some velocity difference from the gas, but basically they will have the same velocity as the gas. However, if we go to larger particles, things with larger Stokes numbers, then they can have distinctly different dynamics from the gas and different velocities. And so what that says is that at a single point in space, we can have particles with different velocities at that same point. Okay, so it's more like a radiation situation where at one point in this room we can have light rays which are moving in all different directions, right? They're not colliding with each other frequently enough. The light rays are certainly not colliding with each other. The particles are not colliding with each other frequently enough to enforce a single velocity field. And here's just actually a nice image from an experiment from a German group. So this is a real fluid experiment where they have particles in that experiment, and they track them with cameras and look at the trajectories. And so if you have particles that are decoupled enough from the gas, they can be moving basically in the same volume with different velocities. So there's a different interpretation or a different implementation where you treat the gas as a compressible fluid, or compressible or incompressible, but you represent the solid component as discrete particles. And these would be, these wouldn't be one particle for each dust particle in the disk. Each of the particles would, of course, represent in reality a very large number of the physical particles. And in this situation, you have to do things a little bit differently. So you then have, this is the gas grid cell. Here are the particles here. And the basic idea would be that you interpolate the gas quantities to the location of the particles, and then you take the particle properties, and you interpolate them back onto the gas grid to treat the momentum coupling terms. And you can then go on. If you want to do self-gravity, you can have some solver for the self-gravity of the solids and for the self-gravity of the gas if you wish. So other studies of these instabilities with Athena and with Pencil have mostly been based on this particle-like description. And of course, it has advantages and disadvantages. It's certainly more physically accurate if you get to these large particles. You have resolution that's different in different places then, because the particles will settle and concentrate, which may be good or not so good. It introduces different considerations for parallelization and so forth, because the particles here can all be concentrated in a relatively small number of grid cells. So there's various considerations. But I can just show you what this sort of thing looks like. So this is nonlinear evolution of the streaming instability, including self-gravity. So here's, this would be the radial direction. This would be the azimuthal direction, the orbital direction. And the colors here that you're looking at are just the overdensity of solids compared to the initial value. So you're seeing initially this instability developing. Different panels are different parameters, which we don't need to get into. And the way it tends to work is that you first produce almost axisymmetric streams of particle overdensity, which are showing up in that rightmost movie first. And then within those, you form dense clumps of material, which can become dense enough to potentially collapse under self-gravity. So we and others are looking at this as a way of making planetesimals. So these are kilometer or 100-kilometer sized objects by concentrating small solids, maybe centimeter-sized solids, into very large clusters, which then collapse under self-gravity. And that's what's happened in these kind of simulations. So this is the kind of thing people are doing. I should say that there are many challenges in this kind of area as well. You've made some dense things in these simulations, but if you asked what's the density of those very dense clumps, it's very, very small compared to the material density of an asteroid or a comet. So in reality, those objects would have to collapse down at least a couple of orders of magnitude more in spatial scale. And so this involves the same sort of multi-scale problem that we were discussing yesterday. And then there's some other problems here. Maybe see this scale here is in units of the disk sail height. These are very small little boxes because this is a fairly small scale instability. So in addition to going to smaller scales to really see things collapsing down to planetesimals, you'd also actually like larger scales to embed this in the context of the protoplanetary disk. So those are aspects that remain to be done for future work. Okay, I think I will stop there and take any more questions. So electric charges on the air. We don't often consider that. The dust particles will be charged. We might have to consider it. So there's various places where we might have to consider it. We might have to consider in some cases the charge carriers could be dust rather than molecules. Okay, so for example, in that plot I made of the different non-ideal MHD regimes in a disk, that made an explicit assumption about what the charge carriers were. Right? And so it would alter things if dust were the charge carriers. There might be some circumstances where the actual electric forces, also are important. I mean, they're certainly important in determining whether things stick and so forth on sort of microphysics at that level. There might be some circumstances where the charge directly matters. Its interaction with the magnetic field matters, but that's not very often considered, I would say, or rarely considered. So I would say the general, I think the most common view is that the jets probably arise from interaction between the stellar magnetic field and the inner region of the disk. Okay, so for sure we know that these are magnetospheric accretion systems. So most cases, at least for low mass stars, the stellar magnetic field is strong enough that it's created a magnetospheric cavity. So the jet launching process close to the star, which is really producing the jet-like structure you see, is probably related to that, or at least involves that at an important level. Okay. Now, there may also be outflows from the disk at lower velocity, further out, and there could be a mixture of both MHD driving, but there can also be thermal driving, because if you expose the disk to EUV radiation, the surface will be 10 to the 4K, so that will be unbound gas, even actually relatively close to the star. And probably the reality is that there's some contribution from MHD driving and some contribution from thermal driving. But that would be a sort of slower outflow. The jet itself, where you're seeing quite high velocities, therefore must come from close in, probably involves also the stellar magnetic field in a basic way.
And what's the range for the Stokes parameter such that the object is considered large enough to be weakly coupled to the field?
Again, that would sort of depend on what problem you're really sort of thinking about, right? For the specific case of this streaming instability, there's sort of a sweet spot where things work well for a Stokes number of about 0.1, and maybe an order of magnitude or a little bit more than that on each side. But there could be other, there are other problems you might be interested in where different regimes of Stokes number would be significant, Okay.
Have you heard of this approach that uses, instead of the two fluids, uses one fluid with a barocentric velocity represented?
Yeah, thank you. So actually, when I was writing these slides, I meant to mention that, and then I forgot. So yeah, so if you like, just like in the MHD case, it's possible to write a two-fluid thing where you have dust and gas, also in terms of a one-fluid description. And so that is in some way a simpler way of getting at, in particular, the dynamics of the situation where the Stokes number is small and you have very good coupling between the systems. So that's another approximation you can make, and I would say sort of in order of physical reality, that's the least realistic, but it's also numerically the easiest. Then having them explicitly as two fluids is sort of more realistic, but more complicated. And then dealing with it as particles is what you need to do if you need very large things, but can be substantially more expensive. So as usual, it's a trade-off as to how you want to spend your computational resources, resolution, and physical effects. Okay. If we have no other questions, I think we should break for coffee.